Hi, I want to welcome you to my today's presentation about cosmetic foams. My name is Lea, and unfortunately I cannot be here in person, but my colleagues welcome you very warmly on our booth from Kinematica. It's booth 210, and if you are interested in contacting me, it's science@kinematica.ch. So anytime you can contact me, and I will start now with my presentation on foamed cosmetics. As I mentioned, I'm a food scientist. I did my PhD in food process engineering, and I did my PhD on foams. That's where my passion is, and that's why I want to talk on foams today. So I started my PhD with protein foams. You see here in the center, nice water-based foams, quite easy to foam. And then I took one step further to fat-based foams here on the left side. These are butter fat foams, and the goal was to have a nice spreadable butter after the fridge, so cold spreading on the toast. And now I took my knowledge from the food process engineering and I translated it into cosmetics. And this comes out here on the right side. It's a cream, foamed cream that we produced with our Kinematica unit. And I will talk about this today. So what is the background here? We saw during my PhD that when we incorporate gas, in this case it was nitrogen, to avoid oxidation of the fat, we can drastically reduce the hardness of the fat. That means the hardness is directly correlated to the creaminess or to the spreadability, and therefore we can say that we reduce the hardness of the fat by 30%. And could be able to cold spread the fat, so the foamed fat. What we also saw is that when we incorporate more gas, so the bigger the gas fraction, the creamier it is. And this makes it really, really interesting for cosmetic industries. So I will talk about this. And now how we did that. So it was with the help of Kinematica already during my PhD. And now it's a technology that compared to the conventional units that are available on the market today, we work at ambient pressure. So we don't work with a extrusion kind of process or a spray process. It's ambient pressure, and therefore we can really nicely control the bubble size. And this makes it even more interesting for cosmetics because then it's more stable. So how does this process look like? It's a dynamically enhanced membrane technology. So we have in the center, we have a cylinder which is rotating. And then the cylinder is surrounded by a membrane. It's a porous membrane. And we give now the gas, so we push the gas through this membrane into the gap between the cylinder and the membrane and into the product. How these membranes look like, I can show you afterwards. But here we can nicely trigger or control the bubble size by the rotation of this inner cylinder, and this makes it really, really gentle. So compared to other technologies, it's decades of reduced energy consuming. We can also produce additive-free emulsions or foams. This is something I can show you afterwards. We can have gas fractions up to 90% and bubble sizes down to 2 microns. And due to this pore structure in the membrane, we can have really nicely narrow distributed bubbles and therefore even more stable bubbles or foams. And this makes it really interesting for the cosmetic industry. And also due to the low energy consuming of the technology, it's ideal for heat or shear sensitive material. How does these membranes exactly look like? So we have sintered membranes here on the left side. Then we have lasered membranes. For the sintered membranes, the smallest we have are around 3 microns. And the laser membrane we have is 50 microns in pore size. And with the laser membrane, every pore has exactly the same size. So when we're talking about 50 micron pores, then all the pores have exactly 50 microns. And with this, you can really create almost monodisperse foams or also emulsions. Here you see it on the right side, you see it again illustrated. So we have the inner cylinder, which is rotating. We have the disperse phase. Here in this case, it's a gas. You can choose the gas. You can take nitrogen, CO2, air, O2, whatever you want, which is incorporated into this gap where the cream is or where your product is. And due to this inner cylinder, the faster we rotate, the faster we have a detachment of the bubbles from the membrane surface and therefore smaller bubbles. So you can really nicely control the bubble size and the throughput. Just a quick comparison to rotor-stator technology. So we in rotor, or in general in foaming units, we have really a harsh breakup. So you incorporate a large bubble and with time you decrease towards smaller bubbles. And with the membrane technology, you just have one breakup at the membrane surface, and this way it makes it way more gentle. How does these membranes look like, or the machines look like? This is a unit we have for a pilot scale unit with around 50 liters per hour, or up to 50 liters per hour. And this one is then a newer device up to 300 liters per hour. Now, just a quick introduction to Kinematica. Kinematica, so you find us on the booth 210. I mentioned that already. It's a company located in Switzerland. So with the headquarter in Switzerland, we are the inventor of the rotor-stator technology, and it's a family-owned business. And we have a global sales in 75 different countries, with the headquarter in Switzerland. We have a company in the US, we have a company in Germany, and one in China. So if you're interested, come to our booth and have a look, and my colleagues are really want to welcome you warmly. Now we are coming to the foamed creams. So the cream that I took was a basic cream, like a one that just a normal cream, DAC, and I incorporated 30% of air into it. Then we work together with a company also in Switzerland, engineering company. They measured for us different properties of the material, and one property is the spreadability. So how much force is required to apply the cream onto the skin. That's why they developed a spreading device that looks like this. We applied the cream onto the top, and then this spreading device is moved with a constant speed over the cream and measures the forces that requires to spread the cream onto the surface. So it measures the force over the distance. And what we saw here is that we can decrease the force requirement or the energy requirement by 10%. So it's easier to apply a foamed cream onto the skin than a normal cream. So the reference is always a normal cream, the same cream, but just not foamed. Yeah. Then the next thing was the penetration into the skin. Here we used a dermaplast. We put cream in it in the same volume. We closed it, so we sealed it. And now we assume that we have, we put it in a climate chamber for 4 hours. And now we assume that we have a mass loss over this incubation time. And this mass loss is over the dermoplast and directly correlates with the penetration into the skin. Here we saw that we have an increased penetration rate into the skin when we use a foamed cream. Again, we assume that we have here the cream or the foamed cream. We have here the plaster in brown, and we have the loss over the plaster, which simulates the skin. And this makes it really interesting for cosmetic and also for pharmaceutical applications, because you have a faster penetration into the skin. You have a better application onto the skin. So if you have an open wound, you have better and easier spreading of the cream onto the wound. A short introduction into the fat-based creams. So if we are working with ointments or with balms, it could be really interesting. You see here on the right side, this is cocoa butter, but what was also done for coconut fat, was also done for shea butter, for palm kernel oil. And we incorporated here nitrogen and created this foamed structure here on the left side. It has exactly the same weight, just that we have here a foamed material, and we have no additives, so no emulsifiers, no stabilizers, nothing added. It's just the pure fat that was foamed, and the foam is so fine that you even cannot see it by eye. How did we do that? It's also with the membrane technology. We have first the pure butter. Then we create a butter paste just by cooling down. Controlled cooling can also be provided by Kinematica. And then we incorporate the foam, also the gas, into this butter spread or into this butter paste. And the gas bubbles are stabilized by the bulk, so by the crystals that are formed. So we saw, as I mentioned at the beginning, that we can reduce the hardness by 30%. So we have we can produce a cold spreading onto the toast, or in this case also we have an easier application on the skin, or maybe also for lipstick. It could be really interesting. Then we tested the same using emulsifiers. We had a look if it's really improving, but we didn't see anything. So you don't need the emulsifiers or the stabilizers. And this is also wanted by the consumer, that we are all more towards natural products. So with this technology, you don't need additives. And here's a CT scan of the microstructure of the foam. And you see that the bubbles are really, really small and nicely distributed. So you even don't see it by eye. So all this was done by Kinematica and mainly by Kinematica Science. It's a new business unit within Kinematica, which has a bigger focus on science and development and innovation. And with Kinematica Science, you can send us your material, and we do the first prototyping on our machines with your material. And for the motto, try before you buy, it's really helpful to understand the right application and to understand what happens in the machine to really be able to give you the best advice. This is a classical procedure, how it works. So we have first an offer and a questionnaire and a talk. You send us your material. We do the trials in our facility. We have a huge lab. We also have a collaborating partners. And then we send you prototypes. but also a huge documentation on the best settings and parameters that you need for your perfect solution. And with that, I want to thank you. So you're very welcome on our booth 210. There you also find other technologies we have, and you can ask about the membrane technology, and they will help you. And you also find SOPAD on our booth. So SOPAD is an inline particle size measuring probe, and we have a probe there, so you can have a look how it looks like, and we really welcome you, and I thank you for your attention and hopefully see you soon. Bye bye.